Okay, so let's see what I was after on this test. So fill in the blank. I was after stoichiometry, or you could use balanced equation as the relationship between the amounts of reactants and products in a chemical reaction. Molarity is the name of the form of a solution concentration that defines moles of solute per liter of solution. Titrant is the thing that we put in the burette. Of course, analyte is the thing that we titrate into. D, I was after products, is the substances that are shown on the right of the reaction arrow in a chemical equation. Aqueous means that a solute is dissolved in water. For F, spectator ion is the ion that appears exactly the same on both sides of the reaction arrow. So actually spectator ions can be removed and create net ionic equations. Gross error is the type of error that depends only on that's the oops error of the investigator. That's gross error. Question 6, I was after equivalence point, is the point in the titration where the stoichiometric amounts of the reactants of each of the reactants have been met. They met each other. I'm thinking I would take equivalence point. Equivalence point or end point. End point is where an investigator believes it would happen. So let me know if you put end point. But I was after hydrocarbon is a compound that contains only hydrogen and carbon. Go figure. J, molecular mass is what I was after is the average mass of a single molecule. K, molar mass then is the mass in grams of 1 mole of molecules. So L. The type of compound that's most likely to form when you have a metal bonded to a non-metal, that's an ionic compound. On to the next page. So these were worth just 1 point apiece. So simply I wanted you to go ahead and reduce C2H8N4. You can divide everything by 2 and you get CH4N2. What is the molar mass of a compound that has a formula weight? Must be an ionic compound, huh? Of 88.0 AMUs, then it would be 88.0 grams per mole would be the molar mass of that compound. Give one example of the oops error, spilling the sample, calculation error, misreading equipment, not following directions. Those are all examples of gross errors. Ineptitude of the investigator. Question 3 were 2 points. Explain why it's okay to use fractional coefficients. And the answer is that if we consider those coefficients not as relative particles, molecules, and formula units, but as relative moles of reactants and products, then you can have a fraction of a mole till the gals come home. Question 4 was worth 2 points. We talked about why yields, you don't get 100% yield, and usually it's biased low, so why you don't get 100% of your product back? And one of them is side or parallel competing reactions. Now, I wasn't as picky as maybe I should have been this semester on this question, but honestly, you describe that phenomenon is a side reaction diverts some of the reactants towards some product that you don't want, and then of course, your yield is going to be lower than you thought. So these are balancing equations. I'm just going to kind of let you kind of check out the answer key, see how that all worked. Now remember, you might have a different set of stoichiometric coefficients if you multiply or divide through by a constant. So remember that all works. Question 6, determine the mass percent of sodium, carbon, and oxygen in Na2CO3. And then so you had to show your work. Good job for showing your work. And I took it as consider we're going to have one isolated formula unit of the compound. The formula mass then is 2 times the molar mass, 2 times the weight of sodium, plus 1 times the weight of carbon, plus 3 times the weight of oxygen. And then that means that the whole formula unit weighs 105.99 AMUs. So then the weight percent sodium would be the mass of the sodium divided by the total mass of the compound times 100%. Give it 4 sig figs, and there you go. Repeat that for carbon and oxygen. So for this one, we had weight percents of zinc, phosphorus, and oxygen in a compound, and we were supposed to come up with the empirical formula for this compound. So if we consider 100 grams of the sample, then those in 100 grams of the sample, those percents, those weight percents would be weight. So that makes zinc, we have 50.8 grams, phosphorus 60.0 grams, oxygen 32.0 grams, just on the basis as we're taking it. So we can use the molar mass of those elements to come up with relative moles, and then we can divide by the fewest, which is 0.517, and you'll notice we have a halvesy here. We have 1.5, 1, and 4. We multiply through by 2, and that bumps up that to 3, this to 2, and this to 4. So the final empirical formula is ZN3P2O8. So pretty good job on that one. All right. So we have a solution of ethylene glycol. The formula is given there, and it is by weight 32.0% pure. That means the rest is water. The density of the solution is 1.04 grams per milliliter. Then we have the question, how many milliliters of ethylene glycol would be needed to make of this solution, would be needed to make a diluted solution with a volume of 225 milliliters and a molarity of 0.255 molar. So make sure that you I jotted down some information up here. I'll need the molar mass of ethylene glycol. I unpacked the weight percent means this, and the density of the stock solution was also given. So I tried to make sure we're dealing with two different solutions. We have stock solution and diluted solution. So notice that I can go ahead and kind of backtracking, see how many moles I needed of ethylene glycol I need in my diluted solution with this volume and this molarity. So I use the volume of the diluted solution, the molarity of the diluted solution. That means I need to transfer 0.0574 moles of pure ethylene glycol. So then if I turn to my stock solution, I'm going to take that moles of ethylene glycol. I'm going to get to grams of ethylene glycol using ethylene glycol's molar mass. Then I consider the weight percent of the solution, and that will give me to grams of solution. Then I use the density of the solution to get to me volume of solution. So 10.7 milliliters solution. The next one was a combustion analysis where actually this particular compound has carbon, hydrogen, and nitrogen. And so you are supposed to come up with the empirical formula. So notice this is the mass of the sample we burned was 0.1156 grams. The mass of the CO2 produced 0.1638 grams, the mass of the water 0.676 grams. Recognizing that all the carbon here in the thing that we burned end up as carbon dioxide, all the hydrogen ended up as hydrogen in the water. So actually we're going to have to kind of go back and pick up our nitrogen here in a minute. So we'll need the molar mass of the carbon dioxide, molar mass of the water. So we can use the mass of the carbon dioxide produced to get to the moles of carbon. Then we're going to need the mass of the carbon to subtract it from the mass of the thing that we burned to get to the nitrogen. So the mass of the carbon is calculated here. We do a similar thing with our water. So to go after hydrogen, we're going to start with our water that was produced. We're going to use the molar mass of water. Recognize we had 2 moles of hydrogen for every 1 mole of water. And that gave us 0.01861 moles of hydrogen. Again, we're going to need that mass of hydrogen here in the next calculation to get to our mass of our nitrogen. So with regard to nitrogen, then we take the total mass of the sample that we burned. We subtract now the mass of the carbon we know, the mass of the hydrogen we know. That gives us the mass of the nitrogen that must have been in the sample. So we can get to then moles of nitrogen by taking that mass, 0.0521 grams of nitrogen, using the molar mass of nitrogen, then to get to moles of nitrogen. Now we're ready to go ahead and set up our little table here. We have carbon, hydrogen, nitrogen. We have the relative moles from our work above. We go ahead and divide by the smallest, which is 0.00372. That leaves us with 1, 5, and 1 mole, respectively, for carbon, hydrogen, nitrogen. So good job. I saw some really good work on that one this semester too. All right. So now we are on to stoichiometry one. Stoichiometric calculation. So we had 6 points possible for A and 3 points possible for B. So the first one notice it says that SCl2 is in excess. We have 9.23 grams of NAF, and the question is, what is the yield of S2Cl2? So it's a simple stoichiometric calculation. We'll need the molar mass of the limited reactant, which is NAF. We'll need the molar mass of the thing we're trying to get to, which is S2Cl2. So down here we have the calculation. We start with the mass of the reactant that's in limited supply, that 0.923 grams of NAF. We use the molar mass of NAF to get to moles. We use the stoichiometry between NAF and S2Cl2 to get to moles of S2Cl2. Then we use the molar mass of S2Cl2 to get to grams of S2Cl2, and that would be our theoretical yield. So a follow-up question looks like this. What if instead of 7.42 grams, what if you only got 1.19 grams recovered? Well, we could do a percent, or we could do a percent yield calculation simply by taking what we actually got back, that 1.19 grams, divided by the theoretical yield, which we got was 7.42 grams. Multiply by 100% and 3 sig figs, that leaves us with 16.0% yield. Pretty low, but who knows? Maybe that's pretty good for this particular chemical reaction. Then the last problem was this the last problem? I guess there's 2 more problems. This problem, if you did your calculations for your lab, that hopefully rang some bells here, because that was kind of similar. So you see I've written in blue underneath the 2 reactants what we know about it. We know the most about the HCl. We have volume and molarity. We have the volume of Na2CO3, but we after the molarity of Na2CO3. So we can use the volume and molarity to get to moles of HCl right here. And then we can use those moles of HCl in stoichiometry, which is a 2-to-1, to get to the moles of Na2CO3. Then once we have the moles of Na2CO3, we can use the volume, which was 25.00 milliliters, to get to molarity. Of course, we need to fix it in terms of moles per liter instead of moles per milliliter. So 4 sig figs, you got a molarity then of 0.1206 molar. Now on to the last problem. So this problem was worth whopping 12 points, 6 points for each part. And if you messed up on the first part, I tried to kind of take that into consideration. But actually, this is one where if you messed up on the first part and you misidentified the limited reactant, the second part wouldn't make much sense. There's different ways of identifying the limited reactant. I'll just kind of show you the one way that I did it. So we were given the mass of SNO2, we were given the mass of BRF3, but you don't know which one you're going to run out of first. So what I did ultimately was to come up with a have ratio versus a need ratio. So I needed the molar mass of those 2 compounds, those 2 reactants right here. And then I needed to know the moles of the 2 reactants. I used the mass and the molar mass to get the moles of each reactant. Now that would be our have moles. So down here, I'll jump to the have. Down here, I took the have moles as 0.0243 moles of BRF3 divided 0.0281 moles of of SNO2. So our have ratio is this right here. Now our need ratio actually came from the stoichiometry. So if you go back up here, we had a 4:3. We had 4 moles were needed for every 3 moles. Yeah, we need 4 moles for every 3 moles. So that's our need ratio. Now when I compare these 2 numbers, notice that I need more BRF3 than I have. So that means that the BRF3 was in limited supply. So now you can answer part B actually. It says what mass of the thing that was in excess, which was the SNO2, was left over. So in order to work this, we need to see, well, how much of my SNO2 was consumed? Well, if I kind of go back to my starting point as moles of BRF3 above, I can use the stoichiometric ratio from the balanced equation, and then the molar mass of the compound SNO2 to go ahead and get grams of SNO2 that would also be consumed. And then how much is left over? I simply take what I started with, that 4.23 grams, and then I subtract from that the amount I consumed, 2.75 grams, and I get, we have, of the excess reactant, we have 1.48 grams remaining. So let me know if you have any questions about